Okay, team, moving right along. Now we're going to talk about continuous charge distribution. So we're getting to a little bit more technical stuff. This is the thing we kind of glaze over in 183 a little bit. We're going to delve in right in 381. The associated reading is 2.1.4. Okay, so if you want to stop the video, read that first, go ahead and do it. The learning objective of this video and probably the next couple, I think I'll break it up, is to learn how to break up a funky charged object into small bits of charge and then set up an integral to calculate the electric field. Okay, so let's get started with that. Okay, right now, so far what we've covered, our current equation for the electric field is this guy here, right? We've got that the electric field is equal to 1 over 4 pi epsilon naught, and we're doing a sum because we're allowing for there to be more than one source charge, but these are all point charges, and it's the charge of each of those point charges divided by the magnitude of our separation vector. I better plug that in. Okay, multiplied by our unit vector. Okay, this, let's just remember, we can only use this. This is for a bunch of little point charges, okay? So just a bunch of little Q's, right? As many as I want to do. All right, but that's kind of a unique charge distribution. We don't deal with that a lot in the real world. We got a bunch of like individual point charges hanging around. Okay, so it's not that useful. Not that useful because instead what we usually want to do is calculate the electric field of some funky charge object, okay? So that could, again, be a spacecraft or a tire, whatever, okay? It's going to be some real object in space that we care about. All right, so let's just draw what that looks like. Here's our funky charged object again, okay? And let's say I want to calculate what the field is at some point in space. So in your book, in the problems, it's just going to draw some point, and we're going to call it P. And this is important, okay? This is not Q, which was, if you guys remember the charge of our test charge, it's not Q anymore, okay? Because we are calculating the electric field, okay, not the force. So there is no test charge at P. P is literally just a point in space. Okay, so let's say we can break up our little funky charged object here into little bits of charge. So we're going to break it up into little bits of charge. And I'm going to say each little bit of charge here has it infinitesimal amount of charge, which I'm going to call dq. Okay, so this is the charge of a bit of the funky charged object. Okay, so I can break it up into a bunch of these, right? And then I can kind of superpose, right, what the electric field is due to a bunch of these little bits of my funky charge object. I still need to do the same kind of calculation. So the electric field from a little bit of my funky charged object is still going to fall off like 1 over r squared. So I still need to know what my separation vector is for that particular point on my funky charge object. That's still going to point from my dq, my infinitesimal little bit of charge on my funky charge object, to the point where I'm trying to calculate the electric field, okay? And now I can write a new equation. This equation allows, okay, for any shape and for non-uniform, which means not all the same anywhere, okay, but continuous, meaning I could describe this maybe a charge distribution with a equation, maybe a two-dimensional equation, three-dimensional equation, but it would describe how that charge is varying across this object. Distributed around the object, okay? Okay, so this equation I'm about to write, it allows for any shape and for a non-uniform but continuous charge distribution around the object. So now what I'm going to do to calculate the electric field is, instead of doing a sum of a bunch of point charges, okay, I'm going to integrate over some charge distribution, okay, and that integral is going to look like this, all right? So this is still going to be the magnitude of our separation vector, okay? But this separation vector, as I do the integral, it's going to change its location, right? Because I am integrating over all the different parts of this funky charged object. So imagine, right, that separation vector kind of scanning over the object. Same thing with our r hat. Let me make that black. Okay, our script r hat is also going to change as I integrate over all of this object. Okay, and the dq here is also going to change. It's going to be the different charges on the different parts of my object. Okay, so this is the general integral that I can set up, okay, for a funky charged object. This dq is the amount of charge in a little bit of it. Okay, this is the magnitude of the separation vector that separates that little chunk of charge to the point that I'm trying to calculate the field. And then this is our unit vector. It's going to point in the same direction, but it's going to have a magnitude of 1. Okay, so that's a pretty equation, but we're still not really done yet. We got a little more work to do before we can do a calculation, okay, because how we do this integral depends on the shape of our funky charged object. And of course, we're going to start off here by going through some general shapes, right? Lines and discs and rings and spheres that are going to make it relatively easy, not easy, but relatively easy to set up an integral that does this, but for that particular shape. Okay, so I'll end this video here, and that's what we're going to do in the next few videos, is show you how to set up those integrals for some simple shapes.